All right. Now remember, I have two ends, right? All right. So now I've got to go to the other end. As x approaches negative infinity, that means I'm looking on the left side of my graph, right? Because negative infinity, if this is my x-axis, this is negative infinity, this is positive infinity. So as I look to the left, what is the graph doing? Going which way? The y, yeah. So it's going up. So this says the left side goes up. The left side goes up. Let's do another one. This is different. Take out your calculator.
You stole mine, buddy. This is mine. What are you talking about? It'd be like $10.
10? Where'd you get that for $10? Because I need about 50 of them.
I could just buy like your phone. Yeah. Literally all calculators. You put 1 + 1.
Go to y equals. Hit y equals. Negative x to the third plus 4 and graph it. Tell me what it looks like. There's a little you want me? Let me hook up my camera. Yeah. Yep. Yep. Zoom. Do a zoom 6 on it. That's what I always try.
It looks like cubic.
Now remember, I exaggerated those humps. You may not see the kind of humps that you expect to see on here.
Gotta put a negative.
Y equals negative. Make sure you use the negative that's below the 3, not the subtraction sign. Negative x to the third. What'd I say? Plus 4. Hit zoom. 6. All right. Describe the end behavior of the graph. So it looks something like this. As x approaches, tell me. All right, let's do negative infinity first then. As x approaches negative infinity, say it. Give it to me in math terms. F of x not equals approaches positive infinity. Why? Because this is the left side going up, right? That's what this is not part of it. I'm just telling you that's what that means. Does that make sense? How about the other side? Yep. Negative infinity. Where are you getting negative infinity from? Because it's going down. That's exactly right. Yep. Now, it doesn't matter. You're only looking at the very ends of it. Yep. Your end behavior, whenever I ask you for it, is always going to be exactly the same. It's going to be this, and then you're going to fill in these two every single time.
What happens if it's like a dot?
We will get to that. Right now, they're not. Now, I want you to look at something. Flip back over to the chart we did at the beginning. Ignoring the constant part, but looking at all the others, do you notice any type of pattern? In behavior-wise. Look at these. This one, the ends go off in opposite directions. This one, the ends go off in the same direction. Opposite, same, opposite. What do you notice about these degrees, though? There is a pattern. What do you think the pattern is? So what kind of conclusion could you possibly draw? Every odd degree, this is very important, every odd degree goes off in opposite direction. Every even degree goes in the same direction. And that leading coefficient is going to be what tells me which way it goes, okay? I'm going to give you a little chart. Put this somewhere very important in your notes because you will want to reference it. You need 4 squares. Even degree, same direction. Yep. Yep. It's not going to be a graph, it's going to be a chart. It is. At the top of each square, yes, that's enough room, Hannah. Now, here's the cool thing about end behaviors. There's only 4 different situations that I could be in, right? Both ends could go up, both ends could go down. They could go in opposite directions this way or opposite directions that way. There's no other possible combination of end behaviors. There's just 4. So if I could figure out based on the equation, I wouldn't even have to graph it to determine the end behavior. So here's what I'm going to do. I'm going to set up a chart. If the degree is even, I know that both ends go the same way, right? Didn't y'all already tell me that, if the degree is even? So these top 2 are going to be even. That means the bottom 2 are going to be odd. Odd always does what? Opposite. Now, the leading coefficient could be positive or negative. Same with odds. Whoa. Every single polynomial in the whole wide world that has an even degree and a negative leading coefficient, or an odd degree and a positive leading coefficient, they have the exact same end behavior every single time. Watch Caleb beside you. Well. All right, so we're going to determine what these end behaviors are, okay? Even positive. Which way do you think they go? You think evens go opposite? Oh, say again, what'd you say? I'm sorry. Up, both ends go up. So everyone that has an even degree and a positive leading coefficient does this. This says both ends go up. I don't have to graph it. I can just look at the equation, and the equation will tell me that both ends go up. How about if it's negative? Down. Both ends go down. Whether I'm to the right or to the left. Both ends go down. I'm going to just give you the odd to save a little bit of time. To the right, the graph goes up. To the left, the graph goes down. And on this one, all right. Ready?
So it's gonna be like questions.
Which one at the top?
The top left.
The top left. It's even and it's positive. So I would be here. Is that the end behavior for this one? Is that what we got before? Look. Say yes, because we did. Look at this one. Negative x cubed plus 4. Which square would I be in? Negative x cubed plus 4. That's odd negative. Here I am. Is that the end behavior that we got? It holds true for anything. So you can look at this and use this as a guide without even graphing the function to tell what the end behaviors are doing. Does that make sense?